Hang on, it's starting now. Yes, we're recording.
I mean,
So of course, this is just kind of this is not really compulsory, this section, because last year we didn't do it, so like we didn't know whether we do it this year, and so obviously this is not testable material. So now they know. Is Kim not coming?
no, just valuable.
This blue one.
Yeah. Yeah, is anyone? Oh, not coming in. No, apparently. Thank you. You're a good friend.
It's a shame because Kim was always making sure that I get everything as it was in the book. Oh, now you're following it in the book?
Yeah,
So it's your job to stop me when I'm saying things that are not like that.
I'm not with Kim. I'm not
Definition. Well, definition. What's definition? Definition, but what I didn't say. So we know the structure of all finite abelian groups.
He's not feeling well.
I'm feeling well. So, yeah, we just last 2 weeks. So now the non-abelian now.
Yeah.
So they are kind of harder, more complicated. And in particular, we won't have a theorem which says every finite non-abelian group looks like this, like we had with abelian. So we'll only really dip our toes into this. So for abelian groups, we studied them using direct products because there was the fundamental theorem of finite abelian groups said that we could get anything as the product of two cyclic groups. Okay, so the two instead of direct products here is going to be factor groups and normal subgroups, and so we define some things related to that. The first one is a subnormal series. So when you get a group G, its subnormal series is a finite sequence of subgroups. You start with the G, and the notation from the book is like this. It has some subgroup, and that has some subgroup, and so on, and then you end up with the trivial subgroup. And then the normal comes from the fact that every next one is a normal subgroup of the previous one. Okay, so HI is normal in the bigger one for each I. Okay, so for subnormal, you just need that this one is normal in that one, and 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 this one is normal in that one. Okay? And if it so happens that all of them are also normal in G, then it's called a normal series. It's not a very important distinction. And the length of such a series is n, which is not the number of groups in it, but the number of inclusions. Yeah, so the number of these Latin symbols. Make sense? Not very deep, a lot of words. Okay. Okay, so if I start with all positive, all integers, in addition, this is just the multiples of 9. This is just the multiples of 45. This is just the multiples of 180. And this is just the multiples of 0. Is that a subnormal series? Yes. No. Is that normal in Z? Everything is normal in the abelian group, so that's normal, that's normal, that's normal, that's normal. So that's not very interesting because they're abelian. If you take something like a cyclic of 24, and you take all the multiples of 2, all the multiples of 6, all the multiples of 12, and just the identity, also a normal series. Again, they're normal because it's abelian. So that's a bit of a boring example. Is that clear though? Okay, it's clear. Anything more? Okay, how about the dihedral? I think you all studied that in coursework, probably. So it has some subgroups like, you haven't submitted the coursework yet. Take note of this subgroup. And this, so this is just 4 elements, and then 1, 2, 3, 4. And that contains just the identity. So what do we call this? H0. This one was H1.
What's in that last bracket, sorry?
This one is H2. This one is H3. Say it again.
It's okay, I worked out.
Okay. What's that? Oh,
Yeah.
yeah. It's an artistic picture of just the identity or the trivial subgroup. It's a good one. I'm going to sell it at auction. Make me at least $1. Okay. So, right. Are they normal in each other? Like in... No.
I've got a reason, but you're not going to like it.
Yeah, give me a reason.
Because it says so in the book.
Yeah, well, okay. So, is this a subnormal series? Like, what is the definition of a subnormal series? H0 must be normal in H1. Well, the trivial subgroup is always normal in anything, so that's fine. H1 should be normal in H2. Can you see an obvious reason why H1 is normal in H2? Because it's index 2. As long as the order of this one is twice the order of that one. They numerous times say that subgroup of index 2 is always normal in the other group, and the same here. It has 8 elements. There's 4, so it's index 2 as well. So they're all normal in the next one. But the book says, and you're right. So this is a normal supergroup, and this is a normal supergroup, and this is a normal supergroup. But what did it say? H1 is not normal in D4. So it's a subnormal series. But not a normal series. Okay? So that should explain the definitions, more or less. Now there's something that is not in the book. So this D4 factor group by second one. What is that group? Do you know? Okay, how many elements does it have? It's index 2. 2. How many different groups do you know on 2 elements? Just one. So this one has to be isomorphic to Z2. Same thing. Well, that's actually equal to H1. Is Z2. So yeah, so somehow you want what do you want? Okay, so for example here, if you took this one out, okay, and just have Z24 and with the multiples of 6 and the multiples of 12 and 0, that's still going to be a normal series. Well, you can add to it, whereas here you cannot add to it. Okay? It's, well, you can't, there is nothing between multiples of 2 and all the numbers from 0 to 23. Because if you put an odd number there, then for it to be a subgroup, you already have to have everything. And similarly here, you can't add anything in between. Could do the multiples of 3, but the multiples of 3 and this, they're incomparable. So you've got multiples of 2, they're not multiples of 3, and you've got multiples of 3, they're not multiples of 2. So it doesn't fit either between them two or between them two. So into this series, you can't add anything. You can't put another subgroup here or another subgroup here or another subgroup here. So it's kind of like you can't expand it anymore. Right? And things like this are called composition series. So the definition is that the definition is somehow different, but it means the same. So a subnormal series for which all the factor groups okay, the factor groups like this are simple. It's called the composition series. Just a companion definition, if you start with a normal series, then what you get is a principal series. If all the factor groups are simple, but we won't be using that. It's just in the book, so I use for completeness. These factor groups called composition factors. So this is an example. All the Z2s are simple, but Z2 is simple. So all the consecutive factor groups are simple. So it's a composition series. More examples. Another example is 13, 16. What's 13, 13, 14, and 15? I've skipped it.
30, 30 showing the assignment.
Oh, don't need that. Read it, but so do you remember that we showed that this is a simple group? Yeah. Nice. And then when you take AN in SN and just a trivial subgroup in this, so this is a composition series.
Can I keep the Yeah, later, please.
No. But I can give you a copy.
How come?
Hmm?
How come I can't keep them?
Because I archive them. I keep a big box with all my group theory notes.
Okay, please give me a copy.
Okay.
Thank you.
It's £2.50 a page. So what's this isomorphic to? Come on. Yes. Why do I write Z3? After, because I got too excited. 3 is always better than 2. Unless it's a group of thugs who are trying to beat you. Then it's better if it's 2 than 3 of them.
Degree classification. 2.
To be honest, it doesn't really matter
To be
anymore.
honest, I just get to pass it.
Like not getting a first is pretty much a failure. Is that everything I wanted to say? Oh no. We're slow. Oh my goodness. Example 13-15. Why is it going backwards? Oh, you brought them. So example 13-15 has Z60. All the multiples of 3, all the multiples of 15, all the multiples of 30, and all the multiples of 0. Is a composition series. This is kind of boring. And then the composition factors so Z6 is this. That's isomorphic to Z3, and you take all the multiples of 3, factored by all the multiples of 15. It's isomorphic to Z5 and 15. Can't be anything else. There's no big proving that it's these, because how many multiples of 30 are there? 0 and 30, okay, within Z60. So there's only 2.
You can't see it.
Oh. Well, you can see something, but not what I'm writing. Okay, so each of them, there's only one group on 3 elements. For any prime number, you know that this factor has order 5, and there's only one group on 5 elements because it's a prime number. So it cannot be anything then Z5. And there is another one. Take all the multiples of 2 and all the multiples of 6 and all the multiples of 12 and all the multiples of 0 is another one with composition factors well, 30 different multiples of 2, so it has to be Z2. And if you take multiples of 2 slash multiples of 6, yeah, it just goes like this. So these composition factors that you get do you notice anything? Yes. What do you notice?
Shadow.
Is that 5? Which one? because how many multiples of 12 are there in Z60? 0, 12, 24, 36, 48. Yeah, so well, I mean, this group has 5 elements. Which is sense, not factoring in by anything. This one has 5 and this one has 10, and so on. So the indices always give you, in this case, the indices of the subgroups give you what it is. Okay? Say it again, what did you notice?
The factor groups are all simple.
Well, yes. They have to be,
It's the same.
otherwise it's not a composition
It's the
series.
same. So it'd be
They're the same, yes. It's principal series as well, that's true. Did you say they're the same, left and right?
Well, I did say it. I thought of me.
Which they are, because there are 2 Z2s, Z3 and Z5, both left and right. Okay, and this is called that these composition series are isomorphic in the book. Okay? So two composition series are isomorphic. Well, he defines it for subnormal series, I think, but we won't need it. If the lists of their composition factors are the same. Like the above. Why do I say lists? Nobody knows what a list is. I'm not saying sets because multiplicities count. Yeah? I want exactly twice Z2 for it to be isomorphic. This one had 2 Z3s and only 1 Z2, for example, they wouldn't be the same because they wouldn't be isomorphic because that would not be possible because that will give you a different group order at the top. But see here, yeah. So I can't say the set of composition factors because that would ignore how often, how many times each of them comes up. Okay, now there's this important theorem, so that's like the most important theorem that we'll get to, I guess, is the Jordan-Hölder theorem. Which is about these things. So if you have a finite group, and it gets 2 different composition series. So the first one is many H's. That's the series number 1. And then there's another one, which is many K's. Might be a different many, not necessarily the same number of, and then necessarily the same length, as we will call it. So that's number 2. then they must be isomorphic. That's Kepson. Does every group have a composition series?
No.
Does the book say?
I'll have a look. Yes, it does. Example 30.17.
Oh, we skipped it.
Yeah, there's one before the table.
Yeah, get some stuff. Does every finite group have a composition series? Yes.
Yeah.
Every finite group is a composition series, which you can kind of, so if the group is simple, then it and the trivial subgroup is already a composition series because it's simple. So you can't put anything. If it's not simple, then you find the normal subgroup which is between the two. And then kind of by induction. So like if you have a group, identity is a composition series if G is simple. Okay. And if not, then it has a normal subgroup which is non-trivial. So N is a normal subgroup of G, non-trivial, so not G and not this. Now, now it's the same thing. So either N is simple. If N is simple, then that's already fine. And you can't add anything in there. If N is not simple, then again you find another group to insert. And this, so now you look at whether G slash N is simple. If it is simple, then that's the start of the composition. That's the start of a composition series. Okay. Otherwise, find a normal subgroup of this factor group, and then it is there because there is this correspondence theorem of subgroups in factor groups that you have with Killian, then you can find some subgroup of G which goes in there, so you can insert. So like this, you can keep inserting. So kind of this is a proof by induction on the order of G. That was just a side remark. It's not part of the. But Z doesn't have one. Like when you look at Z, you can always insert something. Between 180Z and this, you can do 360Z. Between 360Z and that, you can do 720Z and so on. So you can never make like a maximal. No ways to refine it. That's the thing that's good. Look unhappy. Okay, proof can be done in different ways. So I'll do it by induction on the order of the group. What's the smallest order possible? Well, then it has only one composition series. Of length 0 and no composition factors. So that's always isomorphic. An empty list is composition factors. Now assume that the theorem is true for all smaller groups. There are two cases, case 1 and case 2. Case 1 is where second thing on the list is the same on both lists. The first thing is always G. What is the second thing? Might happen that these two groups are the same in both of the series, or it might happen that they're not. So if they are the same, then that's easy. If this one is equal to that one, so then what happens is that you look at what's left when you take the first group out of the composition series. Well, because the second thing on the list is smaller than the first thing on the list, we can use induction, and these two composition series have to be isomorphic. So they have the same list of composition factors, but then the list of composition factors for the first series is obtained by adding this factor group actually equal. Isomorphic. So there are some more. Okay.
These factors, that slash that slash that are exactly the same, maybe in a different order, as these factors. So when you want all these factors, well, you get the ones that appear in this bit and the ones that appear in this bit, they're exactly the same. Then you just have to add that slash that. In fact, you go to your list, and then you get a list for this series. And you add this slash that to the second series, well, to the same one, so you get the second composition factors. Well, but because those are the same, they're both G, and those are the same by the assumption in case one, that factor and that factor is exactly the same group. So when you add it to common list of composition factors, you always get the same list of composition factors, and therefore they're isomorphic. So this is the easy case, and the second case is too hard to do in 2 minutes, so we'll leave it for tomorrow. Any questions? Doesn't seem so.